Alright, in this video we'll be going through the 2022 electricity exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself, once you complete the question or get stuck, unpause the video to see how I go about getting the answer. George is investigating AC circuits. He connects a 54 microfarad capacitor in series with a 36 ohm resistor and a 25 volt RMS voltage with a 50 Hz AC power supply, as shown in the diagram below. Show that the reactance of the capacitor is 58.9 ohms. Alright, so we know that the reactance of a capacitor is equal to 1 all over omega times its capacitance. We know that omega is equal to 2 pi f. Alright, we're given our frequency as 50 Hz, and so therefore that's 2 pi times 50, and so that's equal to 100 pi. Our capacitance is given right here as 54 times 10 to the negative 6, okay? That's 1 all over 54 times 10 to the negative 6 times 100 pi, okay? And that equals 58.9 ohms. And as you can see, that is the value that we're trying to find. Alright, we know that V is equal to IZ, okay, and so therefore the current in the circuit is going to equal to the voltage divided by the total impedance. The voltage is given up here as 25 volt RMS, okay? However, the total impedance, we know that is equal to square root the reactance of the capacitor squared plus the resistance squared, okay? We just found the reactance of the capacitor as 58.9 ohms. And it says right here that the resistance of the resistor is 36 ohms. And so we can simply plug in those numbers, 58.9 squared plus 36 squared, and that equals 69.07 ohms. And so therefore plugging this in, we get 25 all over 69.07, and this gives a current of 0.362 amps. Calculate the phase difference between the supply voltage and the circuit current for the circuit shown on page 2, and state which one leads. You may draw a phasor diagram in the space below. Alright, so we know that the voltage across our resistor is going to come to the right like this, okay? And we also know that the current in the circuit is in phase with the voltage across our resistor. We do not have an inductor in the circuit, okay? As you can see, there's no inductor, so we only have a capacitor. And so therefore, as we know, the voltage across our capacitor is going to lag the voltage across our resistor by 90 degrees, okay? So this is voltage across our capacitor. And so therefore, if we apply vector addition to this phase diagram, we would see that the supply voltage comes down like so. Okay, so this is our supply voltage. And so as we can see, the current leads the supply voltage, okay? And we can find out how much it leads the supply voltage by finding this angle out theta. Okay. Now we know the voltage across our supply, that's our 25 volt RMS, okay? However, what we don't know is the voltage across our resistor, okay? So we don't know the voltage across our resistor. However, what we can do is make this same phasor diagram, however, just with impedance, reactance, and resistance, okay? And so therefore we would have our resistor coming over here, the reactance of our capacitor coming over here, and our total impedance coming down here. Okay, and so this angle is still going to be equal to this angle right here. And so we know the resistance value is 36 ohms, okay? And we know our total impedance is 69.07. Alright, and so therefore if we make a vector triangle off of this, we have our resistor coming like so. Then we would have our XC coming over here, and this will be our Z value right here, okay? And this angle is the one we're interested in, theta. In order to find theta, I'm going to use the value of our resistor and the value of our reactance of our capacitor. The reason for that is because those are the values that we are given, okay? Even though we have the value of the total impedance, we calculated that value, and so there is a chance we might be wrong. In this case, it's actually impossible that we'll be wrong, because in order to find the total impedance, we use the given values, okay? And so unless you put it wrong in your calculator, there is no chance you'll get the total impedance wrong. However, just in general, in exams, it's always good practice to use the values that you're given, if you can, rather than values that you have calculated, okay? Obviously, if you don't have a choice, then you don't have a choice, And so therefore, the value of our resistor is 36 ohms, and the value of our reactance is 58.9 ohms, okay? And so therefore, we have the adjacent and the opposite side, and so therefore, theta is equal to the inverse tan of 58.9 all over 36, and this gives a theta of 58.56 degrees. Explain how the addition of a suitable inductor to the resistance capacitor circuit with an AC power supply can make the circuit resonate. Begin your answer by explaining the meaning of resonance in a circuit. So a circuit is in resonance when the current is at a maximum value, because the opposition to the flow of current, which is called the impedance, is at a minimum value, okay? And obviously this is due to V is equal to IZ. right? If this is at a minimum value, then this will be at a maximum value, all right? And so if we add an inductor to this RC circuit, this is obviously going to become an LCR circuit, okay? And so therefore, if we have our phasor diagram with our voltage across our resistor coming over here, the voltage of our capacitor lagging by 90 degrees, okay? We should also know that the voltage of our inductor leads the voltage across our resistor by 90 degrees, okay? And so as you can see, the voltage of the inductor and the voltage of the capacitor are 180 degrees out of phase. And because this is a series circuit, the current is the same at all points, and so we can draw this exact same phasor diagram without the currents, okay? Like so, alright, like that. And remember, this is only possible because the current is the same at all points, alright? So just remember that the values of our vectors are different, because again, over here we're measuring voltage, and over here we're measuring impedance values. But the shape of the vector diagram remains the same, and that's what we want. So as you can see here, the reactance of the inductor and the reactance of the capacitor are 180 degrees out of phase, and therefore, if the reactance of our inductor is equal to the reactance of our capacitor, okay, their magnitudes are the same. As we can see here from our phasor diagram, their directions are opposite to each other, and so their magnitudes are the same, but the directions are opposite to each other, therefore they're going to perfectly cancel each other out. The vector diagram is going to collapse like so, okay? And as we know, our total impedance is the vector addition of our reactances and our resistance values, and as we can see here, we have no reactance values, and so our impedance is equal to our resistance. And so therefore, because we have no reactance values, our impedance is at a minimum value. We can also see this in our equation where our total impedance is equal to square root XL minus XC squared plus R squared, okay? And so if these values are equal to each other, again, we can see that this value goes to 0. And so therefore, our Z is equal to square root R squared. And so therefore, our total impedance is equal to R. Alright, and so therefore, in order for the circuit to be at resonance, the reactance of the inductor must be equal to the reactance of the capacitor. Alright, David is investigating inductors and magnets. He uses a 1.6 Henry and 22 ohm inductor and connects it to a 12 volt power supply. The inductor can be considered as a pure inductor in series with a resistor, as shown in the diagram below. Calculate the circuit current after 2 time constants once the switch is closed and current begins to flow. Alright, so the way we would do this is we would first find our max current. And our max current happens when our inductor is no longer producing a back EMF, and our inductor acts like an ideal wire, okay? And so therefore, we would have Imax is equal to our voltage all over our resistance, okay? And our voltage is given as 12 volts, and our resistor is given as 22 ohms. And so therefore, this gives a max current of 0.545 amps, okay? And this is also equal to 6 all over 11, okay? So I'm going to use this value to keep whole values for my calculations. Okay, so if we think about the graph shape for our current when we have an inductor, we know that when the switch is closed, that inductor is going to produce a back EMF. And so our current, okay, our current over time is going to start at a minimum value, and it's going to rise to a max, like so. Okay, and we know after 1 time constant, it's going to rise to 63% of its max value. Okay, so after 1 time constant, we have 6 all over 11 multiplied by 1 minus 0.37. And so this is obviously 63%, and this is equal to 0.344 amps. Okay, and so therefore after 2 time constants, which is what we want, we have 6 over 11 times 1 minus 0.37 squared. And this is equal to 0.47 amps. There we go. State the voltage across the pure inductor and the voltage across the resistor once the current is steady. Okay, like I said, once the current is a max value and it's steady, the inductor sort of acts like an ideal wire. And so as we know, if we measure the voltage across any 2 points in an ideal wire, okay, so this voltage is going to measure as 0 volts, okay, between these 2 points in an ideal wire. Okay, and so if our inductor acts like an ideal wire, the voltage across our inductor is also going to be 0 volts. Okay, and we also know this because we also know that once the current is steady, the inductor is no longer going to produce a back EMF. And so we can measure the voltage across the inductor as that back EMF, and we know that back EMF is going to be 0. And so that's going to be 0 volts. And so therefore, as this acts like an ideal wire, and we know that in a series circuit, the voltage is shared amongst its components, therefore the EMF is equal to the voltage across the inductor plus the voltage across the resistor. If the voltage across the inductor is equal to 0, therefore the voltage across the resistor is equal to our EMF, which is 12 volts, okay? And so therefore this is 12 volts, like so. Once the current has reached a steady value, the switch is open and the current falls to 0 in 2.5 times 10 to the negative 2 seconds. calculate the size of the average induced voltage, and state the direction of the induced voltage across the inductor. Alright, so we know that the EMF is equal to negative L change in voltage all over change in time, okay? Now in this case it wants us to calculate the size, and so therefore it does not want us to calculate the direction, and so we can remove this negative. Because remember that negative indicates Lenz's law, and it tells us that the voltage is in opposite direction to the change that caused it. Okay, and so now we can just simply plug in our numbers. We have our inductance value, which is equal to 1.6 henries, okay? Our time is given as 2.5 times 10 to the negative 2 seconds, okay? And our change in current, okay, remember our current falls to 0, okay? And so therefore our change in current is just the max value of the current, which remember was 6/11 amps, okay? And this is because the current falls to 0. And so therefore remember the change in current is equal to the final current value minus the initial current value. The initial current value was whatever Imax was, which is equal to 6/11, and the final value is equal to 0 amps, okay? And so therefore, this is going to equal to 6/11, and remember we just want the value itself, not the direction. Okay, so a negative change in current just tells us that it's going downwards, but we don't really care about that, we just care about the magnitude of the value itself. Okay, and so 6/11 is our change in current. And so now we can just simply plug in our numbers. We get 1.6 multiplied by 6/11 divided by 2.5 times 10 to the negative 2, okay? And so this gives an EMF of 34.9 volts. Alright, as for the direction of this induced voltage, the induced voltage always opposes the change that caused it, okay? And so therefore the induced voltage will oppose the change in the current. As the current wants to drop to a value of 0, it will try to prevent the current from decreasing, and so therefore this induced voltage will act in the same direction as the voltage supply, okay? So it will act in the same direction as our supply voltage. Therefore the induced EMF will try to keep the current flowing in the exact same direction, okay? The 22 ohm resistor is replaced with a 44 ohm resistor, and the switch is then closed. Explain by comparing how much the changes that will take place for the size of the maximum current drawn from the circuit, the time constant, and the energy stored in the inductor once the current is steady. So first of all, our old resistor value is 22 ohms, okay? And our new resistor value, okay, is equal to 44 ohms, okay? And so therefore our new resistor value is equal to 2 times our old resistor value, okay? And so therefore previously our current value was equal to V all over our old, okay? And so now our current value is equal to V all over R new, which is equal to V all over 2 times R old. And we can rewrite this as I is equal to 1/2 V all over R old, okay? And so as you can see, comparing these two, we can see that our current is now half that it was previously, okay? And so we can tick that off. Our time constant is equal to our inductance all over our resistance, and so therefore our old time constant is equal to our inductance all over R old. However, our new time constant is therefore equal to our inductance all over our R new, which is equal to our inductance all over 2 times R old, which just like our current, our new time constant is equal to half our inductance divided by R old. And so as you can see, our time constant is half the value that it was before. And this just means it will take less time for the current to become a steady value. It will take less time for the current to reach a maximum, okay? And so therefore that is this one ticked off. As for the energy stored in the inductor, as the energy stored in the inductor is equal to half Li squared, as the current in our circuit is now half the value that it was before, okay? And so therefore we can quantify this and say that our new current is equal to our old current divided by 2, okay? And so therefore if we make this our current old squared, and this is our old energy, therefore our new energy is equal to half times our inductance times our new current squared, which we can rewrite as our old inductance all over 2 squared, which if we expand this out, we get half times our inductance times our old current squared all over 4. And so as you can see, the energy stored in our inductor will be 1/4 what it was before. Okay, and so you can write that all in. Anne is carrying out some experiments using parallel metal plates to investigate capacitors. She takes a pair of metal plates with an area of 0.16 meters squared and connects them to a 9-volt DC power supply. The plates are filled with air and are separated by a distance of 1 times 10 to the negative 3 meters. Show that the capacitance of the capacitor is 1.42 times 10 to the negative 9 farads. Alright, so we know that the equation for our capacitance is equal to epsilon naught times epsilon times our area all over our distance. Alright, so our epsilon naught is the permittivity of free space. Our epsilon is our dielectric constant, which has a value of 1. And obviously this is our area and this is our distance. So we can plug in our numbers, 8.85 times 10 to the negative 12 multiplied by 1 multiplied by 0.160 all over 1 times 10 to the negative 3, and this gives a capacitance value of 1.416 times 10 to the negative 9 farads, which is equal to 1.42 times 10 to the negative 9 farads. As you can see, that is the value that we're trying to find. Calculate the energy stored in the capacitor once it's fully charged. Alright, so we know that EP is equal to half QV. Alright, that's in our formula sheet. We're not given the charge stored on the capacitor, but what we do know is that Q is equal to CV, and so we can plug this into here, and we get half CV squared, okay? And so now we can plug in our numbers, and we get half times our capacitance, which is 1.416 times 10 to the negative 9, multiplied by our voltage, which, as we know, when the capacitor is fully charged, the voltage across this capacitor is going to be equal to the power supply, and so therefore that is 9 volts squared, and this is equal to 5.73 times 10 to the negative 8 joules. There we go. Describe the effect on the energy stored in the capacitor when a sheet of micro with a relative permittivity of 7 is introduced between the capacitor plates. Alright, so before we just had air, which had a relative permittivity of 1. Okay, so now we have increased the relative permittivity to 7. And as we know in our equation for our capacitance is equal to epsilon naught epsilon times our area all over a d. Okay, this value stays the same because it's a constant. This value has not changed, and this value has not changed. Okay, so the only value that has changed is our relative permittivity, which is this value. Okay, and so we're increasing this value from 1 to 7, and so this is a 7x increase. Okay, so a 7 times increase. And so therefore, the capacitance value will increase by 7 times also. Okay, and so therefore, as EP is equal to half CV squared. If our capacitance value has increased by 7 times, therefore the energy stored in the capacitor will also increase by 7 times. Alright, and then disconnects the plates from the 9 volt DC power supply so that the plates are electrically isolated. She then pulls the plates apart, explain what would happen to the charge on the plates and the voltage across the plates. Alright, so the charge on the plates, nothing happens to that, that just remains the same. Okay, so Q remains the same. Alright, however, if the plates are further apart, that means as our capacitance is inversely proportional to our distance, okay, and that is from this equation right here. We see we have distance right there, okay, so distance right there. So therefore our capacitance is inversely proportional to our distance. If we increase this distance because we're pulling the plates apart, therefore our capacitance is going to decrease, okay? And so therefore as Q is equal to CV, if the charge remains the same on the capacitor plates, but our capacitance has decreased, therefore our voltage must increase. Okay, and so if we think about what this means for a second, if our voltage has increased, okay, so our voltage has increased, that means each coulomb of charge carries more energy, okay? And so if we have the same amount of charge, that means we just added energy into the system. Okay, so where does that energy come from? That energy comes from the work done by separating the plates. So the energy that you do by separating the plates, that gets transferred into the charge, all right? And that gets recognized as an increase in the voltage, all right? Because remember, voltage is the amount of energy per coulomb of charge. And then experiments with connecting some different capacitors in series and in parallel across a 12 volt power supply, as shown in the diagram below. Calculate the voltage across the 1.7 times 10 to the 2 microfarad capacitor. Begin your answer by calculating the total capacitance. Alright, so we can calculate the total capacitance of this system right here, okay? And we know that when we add capacitors in parallel, we just simply add them like so. Okay, C1 plus C2. If you want to know where this equation comes from, I go through it in part 2 of my capacitance videos in my electricity playlist. It's towards the end of that video. And I also go through it in one of my first videos I actually made, so you can go to like oldest and it'll be there. So you can go check that out as well. But we can add this up and we get 6 times 10 to the 2 microfarads plus 2 times 10 to the 2 microfarads. And so that is equal to 8 times 10 to the 2 microfarads. And so that, just to make things simple, is equal to 800 microfarads, which is equal to 800 times 10 to the negative 6 farads. All right. And so therefore, if we were to redraw the system, we have a power supply over here, and we can redraw these two capacitors in parallel as one capacitor, which has a capacitance of 800 times 10 to the negative 6 farads, okay? So this is 800 times 10 to the negative 6 farads, okay? And that is in series with another capacitor, which has 470 times 10 to the negative 6 farad capacitance, okay? And so this is obviously 12 volts still. So now, if we were to find the total capacitance of this system right here, the total capacitance when we have capacitors in series is 1 all over C1 plus 1 all over C2. Again, I go through this exact equation in those same videos, so in part 2 of the capacitance videos as well, if you want to check that out, where that comes from. And so this is equal to 1 all over 470 times 10 to the negative 6 plus 1 all over 800 times 10 to the negative 6. And so this is equal to, oh, I forgot, this is also 1 all over CT. Okay, so therefore CT is equal to the inverse of all this. Alright, and this is equal to 2.96 times 10 to the negative 4 farads. Alright, so now from here we have the total capacitance and we also have the voltage of the supply, and so therefore we can find the total charge. Okay, and so if we find the total charge, remember in series, the total charge is equal to the amount of charge on each capacitor. Okay, and so therefore, once we find the total charge, we can therefore find the voltage across one of the capacitors, which is this capacitor right here. Okay, so the total charge is equal to the total capacitance times the voltage, which is the voltage of the supply, and so that is equal to 2.96 times 10 to the negative 4 multiplied by 12, and this gives a total charge of 3.55 times 10 to the negative 3 coulombs, okay? And so therefore the voltage across this capacitor is equal to V is equal to Q all over C. Remember that the charge on each capacitor in series is equal to the total charge, okay? And so therefore the charge is 3.55 times 10 to the negative 3 all over the capacitance of this capacitor, which is given right here, so we can plug that in. 470 times 10 to the negative 6, and this gives a voltage of 7.56 volts. There we go. And with that, we're done. See you.